On. Load freeze. Mode. Displacement drive. Out. Displacement. Check. Forward. Check. Bank. Check. Gyros. On. Foil angles. 221. Trim switches. Auto. Right sensors. -6, -6. All push. Good. Turbine throttle control. Pilot. Ready for takeoff. Roger. Switching to takeoff now. On in takeoff. Good set. +1.
This is a hydrofoil. She is the descendant of a concept more than 75 years old. But because of modern technology, she now has a bright future in the United States Navy. In the age of speed, we need ships that go fast, no matter what the weather, no matter how high the seas. These ships of the future will have small crews, highly skilled in several areas. Their platform must be stable and reliable, versatile, and easy to maneuver. This hydrofoil is operating in heavy seas, yet she maintains a constant level. A destroyer, fighting the same conditions, slams and labors. Her speed is slowed by the rough water. Conventional ships, like a destroyer, are hampered by the added resistance from waves in heavy seas. But hydrofoils are ships with wings. Their foils create lift, and once they are foil-borne, they experience little drag from their relatively small foil systems. The idea of hydrofoils is not new. In 1918, the HD4 was tested in Canada by her designers, Alexander Graham Bell and Casey Baldwin. And even earlier, in 1898, Enrico Fornanini had demonstrated a hydrofoil which could make 40 knots. The Navy has been studying hydrofoils since the late 1940s. We've put foils on a variety of craft in our search for speed and stability. But this little ship was the turning point for the Navy's program. Sea Legs showed the advantages of a fully submerged, automatically controlled foil system, the type that appeared most capable of meeting the Navy's requirements. There are two types of foil systems: fully submerged and surface piercing. The fully submerged system puts the lifting surface completely below the water. Because lift on the foil is relatively unaffected by the water surface, the ship requires an automatic control system to maintain flying height. Surface piercing foils have lifting surfaces that penetrate the water. Lift varies in relation to speed and depth of foil submergence. This system is fundamentally stable because it is self-righting and is used extensively on commercial hydrofoils. However, the fully submerged system provides smoother operation and greater flexibility in heavy seas. Another major distinction in hydrofoils is the distribution of foil areas along the hull. The canard arrangement puts most of the load on large foils aft. In the conventional or airplane configuration, most of the load is borne on two foils forward of the center of gravity. A third foil is necessary in both cases for stability and control. Foils are built of high-strength materials to make them rugged but light. They are retracted for protection and to reduce draft when entering a harbor. Hydrofoils operate much the way a plane is flown. The pilot house resembles a large aircraft cockpit with autopilot, instrumentation, right and left seats. The helmsman handles the controls like a pilot, and hydrofoil sailors speak the pilot's language: take off, land, fly. Inputs to the automatic control system are provided by height sensors, gyros, and accelerometers. Continuous readings are fed directly through a computer to the foil system. Hydraulic actuators then position the control surfaces to the desired angle. Actual control of the submerged foil differs with each design. On this ship, The entire foil is moved to change the angle of attack or lift. This is known as incidence control.